Preparing for IBM Data Engineer interview questions interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a scalable batch data pipeline for IBM's hybrid cloud environment? I would separate ingestion, transformation, validation, and serving layers. Sources would land immutably in encrypted object storage, with metadata captured in a catalog. Spark or SQL jobs would process partitioned data, while an orchestrator manages dependencies, retries, and backfills. I would expose curated datasets through DFlat2 or a warehouse and monitor freshness, volume, and quality. For IBM's hybrid environment, portable containers, private connectivity, IAM, and clear lineage are essential. While answering, cover source extraction, object storage, orchestration, Spark or SQL transformations, partitioning, retries, monitoring, security, lineage, and deployment across on-premises and cloud environments. Question 2. What is the difference between ETL and ELT, and when would you choose each? ETL transforms data before loading it into the target, while ELT loads raw data first and transforms it using the destination's compute. I prefer ELT when cloud or warehouse resources can scale and analysts need flexible reprocessing. ETL remains useful when data must be cleansed before storage, bandwidth is limited, or strict controls prohibit raw data retention. In IBM environments, the choice depends on DFlat2 capabilities, hybrid connectivity, compliance, and operational cost. Make sure to cover transformation timing, warehouse compute, source system impact, governance, data volume, schema flexibility, and examples involving DFlat2, cloud storage, or distributed processing. Question 3. How would you optimize a slow Spark job processing several terabytes of data? I start with Spark UI and the physical plan rather than guessing. I look for excessive shuffles, skewed joins, tiny files, and scans of unused columns. Then I use Parquet, predicate and column pushdown, sensible partitioning, broadcast joins for genuinely small tables, and adaptive query execution. I avoid caching unless data is reused. After each change, I compare stage duration, spill, input size, and cluster cost, preserving correctness throughout. In your answer, talk about execution plans, partitioning, predicate pushdown, column pruning, joins, shuffles, serialization, caching, file formats, skew, and measuring improvements with Spark UI. Question 4. How would you implement reliable incremental loading from DFlat2 into a cloud data platform? I would prefer DFlat2 change data capture when available because it captures inserts, updates, and deletes reliably. Otherwise, I would use a trustworthy update timestamp or monotonically increasing key, recording the high water mark only after successful commit. Each batch would be idempotent, with deduplication and merge semantics in the target. I would reconcile counts and control totals, retain checkpoints, and design replay procedures for failures or late arriving changes. Be sure to mention watermarks, change data capture, transaction consistency, deletes, late updates, checkpoints, ID impotency, audit columns, reconciliation, and recovery from interrupted loads. Question 5. Explain how you would build a streaming pipeline with Kafka and Spark structured streaming. Kafka would provide partitioned topics, and Spark structured streaming would consume them through a consumer group. I would key events to preserve ordering where required, parse version schemas, and use event time windows with watermarks for late data. Checkpoint locations preserve progress and state between restarts. Exactly once behavior requires compatible syncs and careful transaction design, so I would also monitor lag, throughput, failed records, and route malformed events to a dead letter topic. Focus on topics, partitions, consumer groups, offsets, event time processing, checkpoints, watermarking, exactly once considerations, dead letter handling, schema evolution, and operational monitoring. Question 6. How do you ensure data quality in an enterprise pipeline? I define measurable checks at ingestion and after transformation, null thresholds, valid ranges, uniqueness, referential integrity, freshness, and reconciliation against source totals. Failed records should be quarantined with reasons instead of silently discarded. Critical checks block publication, while lower-risk issues generate alerts. I would publish quality metrics and ownership in a catalog, investigate recurring failures at the source, and use representative test data in C before production deployment. Cover completeness, validity, uniqueness, consistency, timeliness, referential integrity, profiling, contractual thresholds, quarantine handling, alerting, ownership, and reporting quality metrics to stakeholders. Question 7. What strategies would you use to handle schema evolution in a data platform? I treat schemas as contracts and version them explicitly. Additive, nullable fields are usually backward compatible, but renames, type changes, and removals require migration planning. A registry can enforce compatibility for event streams, while batch pipelines validate schemas before processing. I would support overlapping producer and consumer versions, document deprecation dates, and test representative payloads. The goal is controlled evolution without surprising downstream IBM applications or analytical users. Discuss backward and forward compatibility, schema registries, versioning, nullable additions, breaking changes, consumer contracts, migration windows, validation, and communication between producers and consumers. Question 8. How would you model data for analytics using a star schema? I begin by defining the fact table's grain, such as one order line or one daily account balance. Facts hold measurable events and foreign keys. Dimensions describe customers, products, dates, or regions. I use surrogate keys and conformed dimensions so separate facts can be analyzed consistently. For history, a Type 2 customer dimension preserves prior attributes. This denormalized structure simplifies queries and improves reporting performance, although operational systems need different modeling. In your answer, explain grain, fact and dimension tables, surrogate keys, slowly changing dimensions, conformed dimensions, measures, and why the model supports efficient analytical queries. Question 9. How would you troubleshoot duplicate records appearing in a production data warehouse? I would first define what duplicate means using the business key, because identical payloads may represent legitimate events. Then I would trace lineage from source through joins and loads, checking retry behavior, CDC replay, missing merge keys, and one-to-many joins. I would quantify affected partitions, preserve evidence, and repair data with a controlled deduplication job. Prevention includes unique constraints where appropriate, idempotent writes, checkpoint validation, and automated duplicate quality checks. Make sure to cover business keys, ingestion retries, non-idempotent writes, joins, CDC semantics, late data, uniqueness checks, lineage, reproducible queries, remediation, and prevention through pipeline design. Question 10. How would you design data security and governance for sensitive customer data? I would classify fields such as identifiers and financial attributes, then apply least privilege access through roles and groups. Data would be encrypted in transit and at rest, with keys managed separately from applications. Sensitive columns could be masked, tokenized, or restricted by row-level policy. I would capture access audits, lineage, retention rules, and deletion workflows, and review permissions regularly. IBM's governance tooling can centralize cataloging and policy enforcement across hybrid environments. Discuss classification, least privilege, encryption, masking, tokenization, row and column policies, secrets management, audit logs, retention, lineage, regulatory requirements, and access reviews. Question 11. What is data partitioning, and how do you choose an effective partition key? Partitioning organizes data so queries can skip irrelevant files or partitions. I choose a key aligned with dominant filters, commonly event date, while checking cardinality and distribution. A timestamp may support pruning, but I avoid creating one partition per minute or customer. I also watch for hot partitions and small files. The right design balances scan reduction against maintenance complexity, and I validate it using realistic query plans and workload measurements. Cover query patterns, cardinality, data distribution, partition pruning, time-based organization, hot partitions, file sizes, maintenance overhead, and avoiding excessive or skewed partitions. Question 12. How would you handle late arriving and out-of-order events? I distinguish event time from processing time and use event time windows so results reflect when activity occurred. Watermarks define when the system considers a window sufficiently complete, while an allowed lateness policy accepts delayed events. Late records may update aggregates through idempotent merges or correction tables. I would expose data completeness status, retain replayable raw events, and choose the lateness threshold from business needs rather than arbitrary processing convenience. Be sure to mention event time versus processing time, watermarks, allowed lateness, state management, corrections, replay, idempotency, and communicating completeness to downstream consumers. Question 13. How do you orchestrate and monitor dependencies in a data workflow? I model each workflow as a clear DAG with small, observable tasks and explicit dependencies. Tasks should have timeouts, bounded retries, deterministic inputs, and idempotent outputs. The orchestrator records run metadata, logs, row counts, and freshness metrics, while alerts distinguish transient failures from data quality violations. Backfills use isolated parameters and controlled concurrency. I also define SLAs with owners, escalation paths, and downstream behavior when a dataset is late. Discuss DAG design, scheduling, retries, timeouts, backfills, dependency sensors, SLAs, alert routing, logs, metrics, lineage, and preventing partial or duplicate outputs. Question 14. Describe a time you improved the performance or cost of a data pipeline. In one pipeline, daily processing cost grew because every job scanned the full history. I profiled query plans and found missing date filters and uncompressed JSON. I converted outputs to Parquet, partitioned by event date, and changed processing to incremental windows. Runtime fell from 4 hours to 40 minutes, with lower storage and compute cost. I validated row counts and aggregates against prior runs, then documented the change, metrics, and rollback plan. Focus on diagnosing the bottleneck, establishing baseline metrics, evaluating alternatives, quantifying impact, protecting correctness, and explaining how you would communicate the result to IBM stakeholders. Question 15. How would you test a data pipeline before releasing it to production? I test transformation logic with focused unit tests and representative edge cases, then run integration tests against realistic source and target interfaces. Contract tests verify schemas, while quality tests check counts, keys, nulls, and business rules. I add performance and recovery tests for large files, retries, and partial failures. C should build artifacts, scan dependencies, run tests, and require approval before deployment. Production monitoring completes the feedback loop. Cover unit, integration, contract, data quality, performance, security, failure recovery, regression, and end-to-end tests, including representative fixtures and automated C/CD gates. Question 16. What is the difference between a data lake, data warehouse, and lakehouse? A data lake stores diverse raw data economically, often with schema applied during use. A warehouse provides governed, structured data optimized for consistent analytical queries. A lakehouse combines low-cost lake storage with table transactions, cataloging, and warehouse-like performance. I would land immutable source data in a lake, publish trusted dimensional or curated tables, and select serving technology by workload. In IBM hybrid deployments, governance and interoperability matter as much as storage cost. Explain storage and governance characteristics, schema on read versus schema on write, workload suitability, transactional support, cost, performance, and how hybrid IBM architectures may combine these patterns. Question 17. How would you migrate a legacy on-premises data warehouse to IBM Cloud? I would inventory tables, jobs, reports, dependencies, data classifications, and performance requirements before choosing a target service. Migration would proceed in waves. Establish secure connectivity, copy historical data, enable CDC, and run old and new systems in parallel. Automated reconciliation would compare counts, checksums, aggregates, and report outputs. After user acceptance, I would cut over during a controlled window with rollback available. I would optimize workloads after stability, not during migration. Discuss inventory, dependency mapping, compatibility assessment, network connectivity, phased migration, CDC, validation, dual runs, cutover, rollback, security, and cost management. Question 18. How would you explain a complex data engineering incident to a non-technical stakeholder? I would begin with impact. Which reports or decisions are affected, when the issue started, and whether data is missing or merely delayed. I would explain the cause in plain language, separate confirmed facts from investigation, and provide the mitigation and next update time. After restoration, I would share scope, validation evidence, and prevention actions. I would avoid blame and technical jargon, while keeping an incident record detailed enough for engineering follow-up. Focus on business impact, clear timelines, facts versus assumptions, mitigation, ownership, recovery estimates, prevention, and avoiding unnecessary jargon while maintaining technical accuracy. Question 19. What Python and SQL practices are important for a data engineer at IBM? In Python, I write modular functions with clear interfaces, type hints, structured logging, configuration separation, and tests. I handle exceptions deliberately and avoid exposing secrets in logs. In SQL, I use parameterization, explicit columns, window functions where appropriate, and inspect execution plans before optimizing. I also document assumptions and package dependencies reproducibly. These habits make pipelines maintainable across IBM teams, whether they run locally, in containers, or on managed platforms. Mention readable modular code, type hints, testing, logging, exception handling, parameterized SQL, query plans, window functions, transactions, documentation, packaging, and secure coding practices. Question 20. How would you design a data platform that supports both real-time dashboards and historical analytics? I would capture events once in a durable log, then feed a streaming path for low-latency aggregates and a batch path for complete historical recomputation. Both paths would share schemas and business definitions, with raw events retained for replay. A fast serving store could power dashboards, while curated warehouse tables support deep analysis. I would measure freshness and reconciliation between views. A unified streaming architecture can reduce duplication, but batch remains valuable for corrections. Cover streaming and batch paths, shared schemas, serving stores, event time aggregation, replay, consistency, freshness, retention, observability, and trade-offs between Lambda style and unified architectures. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.